Welcome to this video on the answer to the question of why it would be um, stable to keep energy in two different configurations between the large sphere and the small sphere system. Now, if you don't know what I'm talking about, you need to go back and watch the previous video and then come back here and we'll get the answer. All right, so we're going to take a look here at what we call energy configurations, or electric potential energy more specifically. And I'm going to compare and contrast two different scenarios. So the first scenario on the left here, this will be my electric configuration, and over here on the right is going to be my gravitational configuration. Now what I'm going to say is this is the Earth over here, and this is a ball. And in this case over here, what I'm going to say is all this down here is going to be, I'm going to call this a positive source charge. And a source charge is just the source of some sort of electrical field in the vicinity. And the Earth I'm going to call a source mass, which is the source of the gravitational field in this realm over here. Now this ball that I'm going to create over here, I'm going to make it a negative charge. But of course, in the case for gravitational energy, both just have mass, right? There's not negative mass and positive mass, there's just mass. And here on the left, we have the case of a positive charge and a negative charge, whereas I could make the ball positive or negative. Now, if we think about what we know that gravitational force and gravitational field have relationships to one another, right? So we know that equation is true. Now, in this case over here, what we would say is that the ball is in its lowest energy state. So if I say the gravitational potential energy is equal to m times g times h. So if I change the height of the ball to something maybe up here, and I'm moving in this direction to a height that's a position that's higher than it was before, that I am increasing the amount of gravitational potential energy in the system. So I'm going to draw a graph of this, and it would just be this linear graph with the slope equaling m times g. Now in this case over here, when we're talking about a scenario where we're moving the ball higher up, I want you to start to think of it from a different perspective. Instead of thinking of I'm moving the ball higher up, let's think of it from the perspective that I am separating the two masses. So we want to think of that the fact that I could pull the Earth away from the ball or the ball away from the Earth. But what I'm doing here, as I increase separation, what that causes is an increase in the potential energy due to gravity. Now, if I look over at this scenario over here, the lowest energy configuration would be these two together. They are naturally attracted to one another. The electrostatic force would pull them directly to one another. So if I think about it, would it be natural for this negatively charged ball to move away from the positively charged source? The answer is no, it wouldn't be natural. So I would physically have to exert a force on it to pull it up and to move it to this position over here. And so what we're going to say here is that when I separate opposite charges, we have to add that term in there. So when I increase the separation, or I separate opposite charges, what I inherently do here is I increase the electric potential energy between them. Now, I could have drawn this scenario in a different configuration. I could have made the charged source over here and the ball like this and shown them moving apart left to right instead of up and down. But I'm trying to make the analogy here. Now, the interesting thing is that, remember, things will always tend to the lowest state of equilibrium. So a ball, if it's in a place that's kind of unstable, so if I placed it, up higher somewhere here, it would naturally pull down towards the other mass. So masses are naturally attracted to one another. There is no other procedure that I could increase the gravitational potential energy as compared to here. Now, in this case, there can be something different because I'm separating opposite charges in this case that naturally will fall together. So if I change the scenario here and I go ahead and say that my source is positive and I'm going to make this charged ball now also positive, they naturally do not want to be with one another. It will naturally push away from the other positive charge. And so in this case, bringing like charges together will cause an increase in the electrical potential energy. So we have to think about it in the configuration to how they would like to be together. So what we're going to do now is we're going to think about those scenarios where I had the very large object and the very small object. If I have, so let's just take two electrons and I put them opposite ends of this big sphere. There is a certain, these are naturally do not want to be next to one another. So if I pull them towards one another, that's increasing the potential energy between them. So they will naturally go to a state where they find each other at a place here versus here, where they're at the lowest configuration possible. In other words, they are the greatest distance r from each other. Now, if I took those same two electrons and I put them here, well, now I've decreased that distance tremendously. And so I can see here that even with two electrons in each sphere, this has, and we'll call this UEL2, and this one UEL1, I can see that the elastic potential energy of object 1 is much less than the elastic potential energy of object 2. In other words, it would take a heck of a lot of energy to keep it in this configuration compared to this configuration. And so we can see that the distance between them does matter, and that's why I wouldn't necessarily say that having two electrons on this big sphere is the same as having two electrons on this small sphere. Now we are just scraping the very surface of this idea of electrical potential energy, and in the next subsequent videos we're going to take a look at how we might develop our understanding. So I'm going to leave you with a challenge, like I always do, and this challenge is a little bit more mathematical, but not much. So if I look at this scenario over here, and I say that the elastic potential energy, or I'm sorry, the gravitational potential energy is equal to m times g times h, so m times g times h, mg of course is the gravitational force, and h is the distance. How might I write the same concept or an analogous statement for the electrical potential energy of this scenario? How might that line up with this like I have in both cases? Figure that out, and in the next subsequent videos, we'll take a look at comparing and contrasting those two fields.